An elastic collision is one in which zero net work is done by non-conservative forces, indicating that no mechanical energy is converted to non-mechanical forms like heat and sound. In this video, I would like to look in detail at a two-body elastic collision in 1D. So say objects A and B slide along and collide with each other here. The spring I drew is meant to indicate that the collision will be elastic, but there doesn't need to be a literal spring here. It could just be that A and B are made of bouncy material, like say two rubber hockey pucks that will bounce elastically off of each other. We'll be in 1D, and so from here on out, since there really is no such thing as a vector in 1D, I'll be dropping the harpoons and the subscripts, like the subscript x's here. As long as we remember that in an example like this, VA1 would be a positive number and VB1 would be a negative number based on direction. So a main point here will be that if you know the masses of the two objects and you know their initial velocities, the outcome of an elastic collision between them can be predicted with certainty. You can predict both of their final velocities given our principles of conservation of linear momentum and conservation of mechanical energy. So let's set up those conservation equations. For our momentum, we note that the net external impulse on the system consisting of A and B, those two moving objects, that net external impulse on the system can change the momentum of the system, but there is no net external impulse during the collision. They're just exerting contact forces on each other. So the change in momentum of A will be equal and opposite to the change in momentum of B. Momentum will be transferred from one to the other. And so we could express this by saying that the total momentum before the collision, one means before they collide, equals the total momentum of the system after the collision, 2 for after the collision. So that's our statement of conservation of momentum. As for conservation of energy, if this is going to be an elastic collision, then zero net work is done by non-conservative forces. The contact forces between them are purely elastic, spring-like, bouncy. And then our change in mechanical energy would have these three terms: the change in kinetic energy of A, the change in kinetic energy of B, and the change in potential energy between them, probably a spring-like potential energy as they come together. But if our initial moment is before they collide, they come together, convert some kinetic energy into stored potential energy, but then push apart and convert that stored potential energy back into kinetic energy, then afterwards there's no more stored potential energy. It's all been reconverted back into kinetic. We can say that the initial potential energy before the collision was zero, and the final potential energy after the collision was zero. Therefore, the change in potential energy was zero, and all we've done is transfer some kinetic energy from object A to object B, or from B to A. So we could state that like this. We could say that the total kinetic energy of the two-object system before the collision equals the total kinetic energy of the two-object system after the collision. So we have here a system of two equations with two unknowns. Our two unknowns would be their two final velocities, VA2 and VB2. So here's my conservation of momentum equation, written explicitly as mass times velocity plus mass times velocity. And then here explicitly is our conservation of mechanical energy equation. This is kinetic energy of A beforehand plus kinetic energy of B beforehand, etc. So our premise was that we are given their masses and we're given their initial velocities, and that leaves us with these two unknowns and two equations. So this should, in principle, be a solvable system. Two equations and two unknowns. We should be able to solve this and get exact values for the final velocities of both objects. And it's possible to do so. It just takes a bit of algebra. It might take you a couple pages of algebra to solve this system of equations, but you could do it. The math required here is not beyond what we've learned. So with a little effort and perseverance, you could solve this system of equations. I'm going to jump right to the solution, which turns out to be quite nice. Here's the solution to that system of equations. The final velocity of A is given by this expression. The final velocity of B is given by this expression. The VCM appears in there, the velocity of the center of mass, that imaginary point in between the two of them. And the VCM is defined in the way we've always defined it. This is sort of our weighted average of their two velocities. The numerator we recognize as being the total momentum of the system, which has stayed constant through the collision, and the denominator is the total mass of the system. So that's our usual relationship between the momentum of a system and the VCM. And I've defined that just in terms of the initial values, VA1 and VB1. So this is all given information. And so apparently you can get the final velocity of A by doubling the VCM and subtracting A's initial velocity, or get the final velocity of B by doubling the VCM and subtracting B's initial velocity. So it is possible to get a nice solution like this only for a 1D elastic collision. You can't find an easy solution if your objects are moving in 2D or 3D. In that case, there are, let's say in a 2D collision, there would be infinitely many possible combinations of directions for them to go post-collision that conserve both momentum and energy. Infinitely many possibilities if you're in 2 or 3D. So you would need to know more about the collision, like about the shapes of the objects, in order to determine exactly what the outcome will be in a 2 or 3D collision. But in a 1D collision, this information is sufficient. You just need to know the masses and the initial velocities, and we can predict the outcome. So let's try and understand what these equations are telling us. Let's sort of develop an intuitive sense of what these equations mean by looking at a few scenarios.